Okay, this is the 3.3b worksheet, and there are some tricky things that are going to happen. So you should always pay attention. If I'm talking, you should pay attention. But today, pay close attention. And if you get confused, you don't want to not understand today. So if you're confused, make really weird faces, and then I'll ask you where you're. Well, Gavin, you don't need to. You're okay. All right. So it is believed that 12% of Emory High students like lifting weights. I totally made this up. A simple random sample of 90 students yields 16 who lift weights. So first off, where did this come from? I don't know. Somebody told us that, right? So that is our population. Okay, that's our population proportion. So is this categorical or quantitative? Categorical. What question are we asking? We're asking a yes or no question. Okay. So, is this a one-tailed or a two-tailed test? Two, because it doesn't say more or less. It just says we think that the truth is 12, and then we're going to disprove that, whether it's too high or too low. Should we use a simulation or a theory model? Theory, why? We have more than 10 successes. We have 16. And we have more than 10 failures. We have what? 74 failures. Lots of failures. Okay. What would the null hypothesis be? What is equal to? What variable? Pi. So the null hypothesis is pi is equal to 0.12. And then the alternative? Pi is not equal to 0.12. Okay. And then, oh, we're going to have to look up our Rossmann. Is it there? No. Yes. Well, kind of. All right, so we want this one. And we want to do a test of significance. So my pi is 0.12. And my sample size is 90. And then you can either enter the count or you can enter the proportion. So what's our count? 16. Okay, and we want to calculate, but I need to change this equal to. So what is our standard deviation? Oh, shoot. Let's use the formula. What is the formula for the sample standard deviation using proportion? You guys remember? It's the square root of success times failure over n. Do you guys remember that? So it actually is pi times, 1 minus pi over n. All right. So my calculator's on another screen. So we get the square root of 0.12 times 0.88 divided by 90. Okay, and I think I wrote this. Make sure that this square root includes the n. Okay? But the nice thing is we don't actually have to calculate that because it's in the app. So my calculator gave me 0.034, but if I pull up the app, I get the standard deviation is 0.034. Okay? So there is a formula. Oh, what, Garrett?
Is there any way you could share your screen?
Well, yes. You shouldn't have waited so long, Garrett. Remember, you're supposed to tell me I'm dumb.
I can't do that.
Okay, I'm sorry. There you go.
Thank you.
Gary, you're way nicer. The kids in the room here, they call me dumb all the time. Okay, so that is the standard deviation of, is that the standard deviation of the population? No, but the population can't really have a standard deviation, right? It was just a yes or no question. So most people answered no, and a few people answered yes. What's the standard deviation? There isn't one. They weren't. It was a categorical question. You can't take the standard deviation of yeses and nos. So this standard deviation describes the sampling distribution. And remember, the sampling distribution represents running a simulation an infinite number of times and creating this curve that represents all the probabilities of all samples that have the same size. Does that make sense? Okay. So, what is the z statistic? So my percentage is 0.12. Okay. How do you guys remember the formula for z-score? Z equals our p hat minus pi divided by the standard deviation. Now, the formula might not make sense to you, but the idea should be pretty simple. So we expected to get 0.12. What did we actually get when we did a survey? We got 16 out of 90. So 16 divided by 90 is 0.1777. And the z-score describes how far away is that number from the expected value in terms of the standard deviation. Okay, so 0.177 minus 0.12 is going to give me 0.052. What does that number mean? Okay. So we expected 12%. Why? Because that's what somebody told us. They told us that the true value was 12%. Now, when we did a sample, we got 17.7%, which was higher than we expected. How much higher? 5.2%. So our sample was 5.2% higher than expected. Is that a lot? Well, it depends. It depends on how spread out this is. What number describes the spread of the sampling distribution? The standard deviation. And what is the standard deviation in this case? It's 3.4%. What does this mean? The average distance from the average of 12% is 3.4%. So, and these are all samples, right? There are an infinite number of samples inside here. So if every dot represented a person who did a sample of 90 people, and everybody got a percentage, on average, you guys would have a distance from 12% of about 3.4 percentage points. That you kind of remember in chapter 2? Okay. So what do we do with that 3.4? So we take our sample percentage, we subtract our pi, and that gives us 0.52, and then we divide that by our standard deviation, 0.034. So 0.052 divided by 0.034. And I get a z-score of 1.5. What does that mean? Our sample is 1.5 standard deviations away from the expected value of 12%. Is that unusual? It's getting there. It's getting close to unusual. What percentage of people are between one standard deviation to the left and to the right? 68%. So 2/3 of the people are within one standard deviation. We're a little farther than that. We're 1.5 standard deviations. Now, if you look on our app, you will see, as soon as I get rid of all of this, you will see a, oh, the z-score is different. Did I mess up? Sample hat, 0.177.
It's 5.7, not 5.2.
Oh, well, that's why. Okay. So they got a standard deviation of 1.69. I just did my calculation wrong. Sorry, guys. And, sorry, I'll show you I'll show you my mistake. I divided by, so 0.057 divided by 0.034. There it is. Now, is that unusual? It's getting close, but this is a two-tailed test. So in a two-tailed test, it's harder to reject the null. And if we look at our p-value, we get a p-value of 9%. So that is number 7. Our p-value is 9%. Number 8, is there evidence to suggest that there is a difference between our sample and the assumed proportion? No. So whoever told us 12%, we go back to them and we say, there is no statistical difference between what we found in our sample and your claim of 12%. Okay? So now we're going to move on to sample average, sample mean. Okay? Which means we have to ask a different sort of question. A large ranch takes 1,950 calves to the auction. Will, you jealous? Think of all those horns you'd be dehorning. That's a big day. Okay, the average weight of the calves is 987 pounds with a standard deviation of 85 pounds. A random sample of 120 of those calves is taken and the average weight of the sample is 978. Okay, so is this categorical or quantitative? Quantitative. The answer is a number. And that number can be averaged. And the idea is the same, but the calculation is going to be a little bit different. So, if we created a sampling distribution, what would the standard deviation be? Okay. How would we find the standard deviation of the sampling distribution? It was in your 3.3 Sci book. So, I'll pull that up and show you guys. So many formulas. And it's a Monday. And this formula is actually kind of nasty, so I don't blame you for not remembering it. All right. Look how terrible that is. So, in this case, we have that. What variable do we use for the standard deviation of a sample? S. What is the standard deviation of the population? Sigma. Okay. So in this case, what is the variable for the population average? So mu in this case is 950. Okay. Sigma in this case is 85. And then what do we call the sample average? X bar is 978. And then S is the standard deviation of the sample. Okay, now you will have to remember those. Do we know the standard deviation of the sample? No, it didn't tell us. Okay. So, the formula for the standard deviation of the sampling distribution is the SD is equal to S divided by the square root of N. Okay. Now, I didn't tell you the standard deviation of the sample. I probably should. So let's say that that is 90. So this is everybody, right? So let's say that I'll add this to the worksheet. So let's say that S is 91 pounds. So we do a sample of 120 calves. We get a sample standard deviation of 91. Okay. So we are going to take 91 and divide it by the square root of 120 because that's how many calves were in our sample. 8.3. Which means that 978, this distance here is 8.3 in our sampling distribution. Okay, so what is the z-score of our sample? Well, how far away was our sample from the expected value? So what is the formula for z-score? And p hat is our proportion. So in this case, it's going to be x bar minus mu divided by the SD of the sampling distribution. Okay. So 978 minus 987 is, what is that, -9? Does it matter which order I put those in? It does. Does my z-score need to be negative or positive in this case? It needs to be negative. Why? Because our sample was smaller than our mu. Okay? And what do I do with -9? I'm going to divide it by 8.3. So -9 divided by 8.3 gives me a z-score of -1.08. -1.08. Okay. What is the probability of getting a sample value at least as far from mu as our value of x bar? There's a word for that. What do we call that number? So here is my sampling distribution, right? And my sample gave me 978. And then the SD of that was 91 pounds. Well, sorry. I guess the SD of my sampling distribution is 8.3. Okay? So, oh, I wrote the wrong number in here. Go away. This is 987, and I ended up with 978, and that gives me a z-score of -1.08. So I want to know what is the chance that I land here or farther that way. Well, that's just the area. That's just the p-value, right? So let's do this. Now, when you do a test of significance, we have the choice between 1 proportion, 1 mean, 2 proportion, and 2 means. So I'm going to select 1 mean, and notice my pi turned into mu, and my population mu is 987. Okay, and then is this one-tailed or two-tailed? It doesn't say. Okay, so we'll do not equal to. My sample size is 120, and the average of my sample is 978, and my sample SD is 91. Okay. Oh, but this question asks at least as far, right? So 11 asks, what is the probability of getting a sample at least as far? So I do need to change this to less than. And you see I get a statistic of negative 1.08, and I get a p-value of 14%. Okay, but notice it doesn't call it Z. That's going to come up in a minute. It called it T. Okay, so that was, so 12. Is our sample value of 978 unusual? No, it's not. Okay, 13. What effect did the size of the population have on our calculations? So this number here, what effect did that number have on what we just did? Where did I use 1950? So I would have used that to get the average of the original, that's true. But sample size did matter. In fact, if you are sampling in California versus Utah, so California has, I don't know, 65 million people in it, and Utah has 3 million. If you want to do a presidential election survey, California is bigger. Do you need to talk to more people in California than you do in Utah? No. None of the formulas use that value. It all has to do with sample size. Now, there is an exception to that. If the number of people you talk to is a significant portion of the population as a whole, that can mess things up. So if there are 5,000 people in a state and you talk to 3,000 of them, that's going to mess things up because you talk to most of them. And then you have to do different formulas, but you don't need to worry about that. So as long as your sample is small compared to the population, the size of the population doesn't matter. So if there are millions of people in the population and you talk to 1,000, that's good. If there are 1 million people in the population and you talk to 1,000, that's good. Okay, I think the book said like 10 times or 20 times as many. I don't remember. So as long as this number is small compared to that number, everything we're going to teach you is fine. And if it's not, I don't know what to do because it's part of a different class, not this class. So sample size matters, population size does not matter. Okay, 14. Would it make sense to run a hypothesis test to check the population average against our sample average? Should we set up a mu and a null and an alternative using mu and test it? No. Why, Jacob? It doesn't make any sense here. What is the point of a hypothesis test? To see if the original claim was true, right? So let's look back here, and I hope this clicks for you. We did a hypothesis test to see whether or not that claim was true. Where did that claim come from? Somebody just gave it to us, right? And we decided what about that 12%? We don't have enough evidence to say that you're wrong. Okay, does everybody get that? We wanted to know if 12 was true, and in the end we said, we can't tell that it's not. All right? So let's go down here. Would it make sense to use this number to tell if that is true? No. Why? It is true. Right? 987 is a parameter. That is mu. So if you've already weighed every single cow, does it make sense to weigh some of the cows to check to see if the original weight of all of the cows is correct? No. Okay? So this number is not going to disprove that number because the 987 is true. That is the population parameter. Does that make sense? So that's going to cause us some problems because our formula is going to require us to have the sample or the population standard deviation. Okay, so when we did this, the square root of pi times 1 minus pi over n, the standard deviation of the population comes from the proportion itself. Okay, but in the real world, are we going to know what this is? No. Somebody's going to give us a number and tell us it's true, and that's fine. We can work with that. Okay? But will we know this number? No. And that's going to create some problems for us. I'm interrupting again. You need better friends. They're not your friends? Okay, so we're going to have to make this huge leap. We need to know what the population standard deviation is. However, if we know what the population standard deviation is, that means that we know what the population average is. And if we know what the population average is, there's no point in doing a sample. Does that make sense? So, in order to calculate a z-score, I need this number from the population. But if I know that number, then I know this number. And if I know this number, there's no point in doing a sample. Does that make sense? Why would you do a sample when you've already talked to everybody? Okay? So what we're going to do is we're going to invent a new test that takes that into account. Okay? Z-tests are great. So 14 is no. Suppose we increase our sample size to 400 and we get the same sample average. If we created a sampling distribution, what would the standard deviation be? So this time it's going to be 91 over the square root of 400. So 91 divided by the square root of 400 is 4.55. Why did it go down? So the more people you talk to, the more cows you weigh, the narrower your sampling distribution becomes. Okay? All right. What is the z statistic of the new sample? So that would be negative 9 divided by 4.3? 4.55. So negative 9 divided by 4.55. And now I get a z-score of negative 1.97. we were 9 pounds, our sample average was 9 pounds lower than our population average. Okay. What is the probability of getting a sample at least as far away? That's going to be, so we need to change this to 400. And I get a p-value of 2.4%. Should we reject the null? No, there is no null, right? So if we rejected the null, we would say, wait a minute, rancher, you claimed that the average weight of your cows was 987. We have just proven that 987 is higher than the actual value using our sample. And then the farmer's going to say, wait a minute, I weighed every single cow. 987 is true. Your sample cannot disprove it. All right. So is our sample value of 978 unusual? Yes. It is unusual. Okay. So, a woman claims that she gets at least an average of 7,000 steps per day. On 35 random days throughout the year, the number of steps she takes are recorded as an average of 7,124. And the standard deviation of her sample is 562. So in order to run a z-test, we need two things. We need to have at least 30 items in our sample. Do we have that? Yes. And we need to know the standard deviation of the population. Do we know that? No, we don't. So this standard deviation is linked to that number. What is the standard deviation for that number? We don't know. And because we don't know, we can't do a z-test. We have to do what is called a t-test. Now, what's the difference between a z-test and a t-test? One has a z and one has a t. So if this is the standard normal curve, okay, and I've told you that the standard normal curve, this is 1 SD, and so on, okay? There is only one standard normal curve, but there are an infinite number of t curves. They're called student curves because student starts with a t. I don't know why. So if you hear me say a t-test or a t-curve or a student curve, they mean the same thing, okay? So if you only have 2 people in your sample, then you're going to get a t-curve that looks something like this. It's going to be wider and shorter than a standard normal curve. If we have 3 people, then the curve is going to get a little bit taller. So it'll start a little lower and then get a little bit taller. And if we have, say, 30, we're going to start a little lower and be a little bit taller. And the bigger your sample gets, the closer this is going to approach your z-curve until you reach the z-curve. When the number of people in your sample is infinity, then the t-curve and the z-curve are the same. Now, luckily you don't need to know any of that, okay? You just need to know that we're running a t-test. Why are we running a t-test? Well, in order to run a z, we have to have 2 things. We have to know what is the standard deviation of the population, and you have to have at least 30 people in your survey. Now, what is the chance of actually having the standard deviation of the population? 0, right? If you know the standard deviation of the population, you also know the average of the population, and there's no point in doing a test. So we're always going to be running t-tests with sample average. Okay. So what do we do? Okay, so number 20 is a t-test. What is the difference between the z distribution and the t distribution? The t's are wider and shorter than the z. And you don't need to write this down, but there's only one z distribution, and there are an infinite number of t distributions. Okay. If we run a t-test, will it be one-tailed or two-tailed? Look at the original claim. One-tailed because she said at least 7,000. Okay. Should we use simulation or a theory? We're going to use theory. In fact, we're always going to use theory when we do a t-test. Okay. What would the null hypothesis be? So H naught says what? What variable are we going to use for population average? Mu. So mu is equal to 7,000, and H sub A says mu is greater than 7,000. Okay. So what is the SD of the sampling distribution? So the SD is going to be the standard deviation of my sample divided by the square root of n. So 562 divided by the square root of, I guess I should have looked at that. What was it? 35. And I get essentially 95. So my SD is 95. Okay. Now, a t statistic or a t-score is calculated in exactly the same way a z-score is. But we call it a t-score to remind us that we have to use a different curve. We can't focus on the z curve, we have to focus on the t curve. And every t curve is different. Which t curve are we going to use? We're going to use the one for 35 in our sample. The 35 curve looks different than the 34 curve, which looks different than the 33 curve, and so on. Okay? So, my t-score is going to be 7124 minus 7,000 divided by 95. So essentially, it's just 124 divided by 95, and I get a t-score of 1.3. Now, do you remember where we drew the line with a z-test? 1.65? You guys remember that? That only applies to z curves. With t curves, it's different, because the more people you talk to, the taller your sampling distribution is going to be, and so your t value is going to be different. So we can't look at a t-score and accept or reject, because every t-score uses a different curve. So we're just going to use that theory model and have it do the work for us. So 7,000, and we want greater than, and 7124, and my sample size was 35, and my average, oh, oops, what am I doing? What am I doing? This is where 7124 goes. And my sample standard deviation, I don't remember what it was, 95? Okay. Okay, so look at this. What did I do wrong? I've done something horribly wrong. Or either that or I calculated this wrong. So, oh, 562, that's why. $562. Okay, so I get a t-score of 1.31, and it gives me a p-value of 10%. Okay, so will I reject the null or accept the null? I will accept the null. So what do I tell the woman? No. Do we think she's right? No, which is weird. She claimed 7,000. We did a sample and got 7,124. Is that enough to prove that she gets at least 7,000 on average? No, it's not. We're going to accept the null, which means we don't think it's greater than 7,000. Okay, now a couple things. Remember how I told you that every t-curve is different? The t-curve is based off of something we call degrees of freedom. So the shape of this particular curve is based off of 34 degrees of freedom. Maybe. So 34 is simply 35 minus 1. So which t-curve do we use? We use this minus 1, which is weird, but that's how they do it, and I honestly don't know why. Now, there are more complicated formulas where the degrees of freedom are a little bit harder to calculate, but if I change that 35 to, say, 34, okay, let's, all right, I'm going to write this down. df equals 34, t equals 1.31, and p equals 0.1003. I'm going to change this to 36. Okay, so now my degrees of freedom says 35. My t actually went up a little bit, so I need to bring this down just a hair. Okay, look at that. This curve has a matching t-score, but do you see how the areas don't match? It's because we're using a different graph. The 34 graph is different than the 35 graph. And that's why we call it a t-score. So you remember not to use the z curve. Okay. So, number 30. If we increase our sample size to 90 days and we get the same sample average and standard deviation, is that evidence against the null? So let's change this to 90. And I gotta go back to 4. Now I get a t-score of 2.09, and my p-value is now 2%. So if we change our sample size from 35 to 90, and we get the same values, now what do we tell the woman? We think you're right. We think you do get more than 7,000 steps per day. All right, on the back side are 3 problems, 3 situations that you need to do a t-test. So you'll need the Rossmann one chance. And don't forget that you need to go up here to scenario and switch from one proportion to one mean. All right, get to work.